So we made it to notebook 3. We introduced Marimo and IBIS. And now we're going to apply these tools to an incident response scenario. And we're going to try and create a notebook that you can use to identify process injection. So we wanted to narrow it down a little bit because you can't cover everything about memory forensics, but process injection is a cool case or cool use case for memory forensics because that's not something you can necessarily find through EDR alone or live tools because the malware can use different techniques to hide itself from the live tools. So we're going to assume that you have a case where you have a system that's been acting weird. You don't know why. You check the EDR logs. You can't see any processes that seem out of place. But for some reason, you have reason to believe that process injection happened. So you went ahead and you acquired a memory image from that system, and you moved it to somewhere where you can analyze it. You ran some volatility plugins. You exported the output to Parquet, and now we're ready to use our notebook tools here and create a powerful app for that. So the goal is not necessarily to create a notebook that can solve all process injection problems, but we wanted to kind of show how you can apply how powerful it is to combine some subject matter knowledge with these tools, and that can help you create useful notebooks that you can use in your organization or your projects with relative ease. So this notebook has a lot of information in it because, like I said, we're going to apply some subject matter knowledge. We already showed how you run some of the plugins, and some of them are not that hard to understand, like PS list, for example. You list out the processes, but some of them are kind of more difficult to understand, like malfind. How does that actually work? So it's useful to have some background knowledge about it before we're going to try and use the output in a good way and kind of make the important information pop. So we're going to go through like different process injection techniques a little bit and then cover some of the plugins that we wanted to use in this particular use case, so that we know enough about the plugin to actually extract the important information from the plugin output that you want to highlight to your analysts. So, but you also have this notebook for yourself for later, so you can go back and visit it. The volatility project is also open source, so you can also look at the actual code to find out how the different plugins work. We included some information here, but maybe you want to look up some other ones. That's great. And then, so after we have gone through how some of the plugins work and why that can detect some of the process injection techniques, we're going to apply some of that information to the data frames that we got from the plugins, and then we're going to find some things that we want to highlight and create a little dashboard for it. Just quickly before we even start digging into the memory forensics parts though, I want to say that before you start doing any of this stuff, you definitely want to run Yara against the raw memory, in case you have a good Yara signature base, maybe from your threat intel vendor or something like that. That's going to be extremely helpful to narrow it down. I know it's very easy to get carried away when you're an incident responder or a security analyst and be like, oh, I want to run all the plugins and like really dig into the bits and bytes. Sure, but before you do that, run Yara and also run strings. Never skip strings. There's like some options that you can use with strings to get both the Unicode and the ASCII strings, and you can also get the address, so definitely do that. Output all the strings, just look through it to get a first impression. That's definitely not enough to figure out what happened, but you should always run strings. But yeah, let's get into it. So like I said, we're gonna only look at process injection here. you already ran PS list, you looked at the output, you can't see that anything that looks like what we, for example, wrote here, CMD spawns really bad program exe. There's none of that. Everything seems like legitimate processes on the system. So here comes the subject matter knowledge part that we actually need to get the job done in this notebook. We're gonna go through one technique now called remote DLL injection. It's the most common one. So in this scenario, the malware exists in a DLL file on disk, and there's an attacking process that wants to inject that DLL into an already running legitimate process on the system. So the attacking process is going to give itself debug privileges so it can read and write to the victim process's memory as if it were a debugger. Then it's going to open a handle to the victim process, allocate memory there, and write the full path on disk to the malware, the DLL that contains the malware. It's going to also create a new thread in the victim process and have that thread invoke the load library function with the DLL path. And then optionally afterwards, it can free the allocated memory that holds the path to the executable because it doesn't need it anymore, and also close the handle. But that's optional. But that's pretty common because it makes it harder for us defenders. So in this case, the detection methods are not necessarily it's not necessarily going to be picked up by, for example, malfind. We're going to see why later. First of all, it is nice for us defenders when they actually use the load library function, because then the malicious DLL is going to be among the loaded DLLs if you run the DLL list plugin. So you can actually see all the loaded DLLs on the system if you just run this. However, you're gonna kind of have to know what process you're looking at, because if you run DLL for the whole memory sample, in this case, we have 8,500 loaded DLLs. So we're not gonna go through this. But even if you know what process you're looking at, I'm just gonna pick a random PID here now, like this or whatever. Even this process has 138 loaded DLLs, and it's not that easy to know which one could be malware. You're going to have to know kind of the baseline for that process already. But that is at least nice to have a look at this if you know kind of the process and you want to just check if there's any DLLs here that seem out of place. That said, however, if the malware unlinks the DLL from the list, because the DLL list plugin relies on a linked list in memory that holds all the DLLs that are loaded for that process. That can be manipulated, and the DLL can be unlinked. So if you want to avoid that problem, you can use the LDR modules plugin. That could also be interesting for you as an exercise for the reader or the participant to compare maybe the output from DLL list plugin and the LDR modules plugin for the processes, and check if there are processes that have DLLs in one plugin output and not the other. For example, if you find DLLs that are loaded in the LDR modules plugin output, but they aren't listed in the DLL list plugin output, that's kind of suspicious. Just food for thought if you want to do that later. But yeah, just to describe, like, it's not that easy to find out if a DLL was injected through remote DLL injection. However, it's valuable to use this plugin output. One detection opportunity as well is if the DLL on disk is packed, which is also quite common because it would want to avoid being detected by anti-malware. If the DLL is packed on disk, and when the load library function loads that DLL into memory is going to have to unpack that packed DLL before it can run it, and then it will have to allocate an executable memory region as well, where it can write the unpacked DLL to. And in that case, malfind can find it. So let's have a look at malfind now to see why that is. I'm just going to remove this again. Yes, okay, so malfind will go through all the VAD regions, and it will flag VADs based on a couple of criteria. First of all, the memory region has to be private. That means that it's not backed by a file on disk. And in addition to that, it has to have the VAD-S tag, meaning that it's a small heap allocation. These two, at least for me, we're going to see that later, but these two are they are very much overlapping, these two criteria. So either that or the memory region has to be backed by a file and have a protection string different from page execute write copy, which is what it will have if it's from a legitimately loaded DLL. So second criteria is that the region has to be there has to actually be bytes to execute there, meaning that it has to be fully committed. We're going to see that also in the malfind output soon. This is different from memory being reserved. So if it's just reserved, then there's no actual memory behind the VAD. It's just reserved. If the memory region is executable but not writable, then it has to have at least one dirty page. So we're going to see very shortly just how it looks. Yeah. It does also flag legitimate processes sometimes because legitimate behavior can be very similar to process injection. So that's why malfind also has false positives. And part of the job when you do memory forensics is to find the true positives. There are other techniques as well. This next one that we're just gonna treat very shortly is remote DLL injection using the queue-user APC function. This is kind of like a remote DLL injection, but it's targeting a thread instead of a process. So it's going to call the queue-user APC API and then use load library and the DLL path to have the thread load the DLL next time it enters the alertable state. So it's like process injection. It is process injection. It's like injecting into a new thread, but it's going to inject into an existing thread. So it's going to be detectable in the exact same way as the previous technique. Next, there's remote shellcode injection. So in this case, it's going to start the same way as with the DLL injection. The attacking process is going to give itself debug privileges. It's going to open a handle to the victim process, but it's not going to call load library because it wants to avoid having the DLL appear in that list that we saw earlier. So the attacking process is going to allocate memory in the victim process with page execute read write protection and just write executable code to it directly. Remember, the first technique would write a file path on disk to that region, so it didn't have to be executable in that case. In this case, it needs to be executable because we're writing executable code directly to the memory region. And then it's going to call create remote thread and point to that address of the memory region where the executable code was written. So remember how we saw that malfind detects memory injection? In this case, the page has execute read write protection. Let's go back and visit it actually. Uh, so the first criteria is definitely satisfied. The memory region is not backed by a file on disk because it is not a file on disk, it's just executable code. It has the VADS tag because it's a it's a small heap allocation. There are bytes to execute, and the region is executable. Next technique, reflective DLL injection, is kind of a combination between remote DLL injection and shellcode injection. In this case, the attacking process will allocate memory within the victim process and write a full DLL image to that region, as well as what we call a small loader stub. And then it's going to create a thread with the address that it wants that thread to execute to be that loader stub. The stub is going to do the same things as the load library API does, but it's not going to register the loaded DLL with the Windows loader. So the DLL will not appear in the DLS list plugin output. However, the LDR modules plugin output will probably find it because that works in a different way, like we discussed earlier. More specifically, what that plugin does is to scan for all DLL process or DLL structures in memory instead of walking that linked list. But as we understand now, it's going to be an executable memory region, so it's going to be flagged by malfind. And a famous attack framework that you probably heard about that uses this technique is Cobalt Strike. Lastly, we also wanted to mention process hollowing. That is a sub-technique of process injection, at least if you refer to the MITRE attack framework. What is done with this technique is that the attacking process is going to create a new process in suspended state. It's then going to unmap the original image of that process and write a malicious image into that memory and then resume the process. Malfind will not detect this, but there are other plugins that will, namely hollow processes. You can have a look at the source code for hollow processes and figure out why that works if you want to. Yeah, I'm not going to spoil it actually. You can go ahead and look at it in the volatility source code. But there is a different plugin here that we're going to make use of, and that is suspicious threads. So what this plugin does is that it's going to look at the threads and it's going to flag them based on these criteria. As long as one of them fit, they're going to be flagged. So if the thread is running from a memory region that is not backed by a file on disk, so the start address of the thread is from a part of memory that is not a file on disk. As you can see, this is not gonna flag a remote DLL injection because in that case, the thread is gonna have an actual file on disk that backs that memory region. Second criteria is if the memory region where the thread starts has unusual protection flags, meaning that the protection flags are different from page, execute, write copy. As you probably remember, those are the protection flags that legitimately loaded DLLs have, and that would be like any DLL that a process needs to function. And the last criteria is if the VAD that hosts the thread maps to a completely different executable than the executable that the thread actually is supposed to be. And that pretty much exactly fits what we said that process hollowing is. So that's why we also describe how this plugin works here. So let's move on to using this knowledge to actually build some dashboard components. Let's have a look at the malfind output here a little bit manually with the knowledge that we just got before we move on to doing it programmatically. So here, as you can see, we already ran the malfind plugin. We exported the output to Parquet, And then we loaded it into this notebook and we renamed all the columns to snake case to just be a little bit more Pythonic. We can see here that there are 214 rows, which is a lot, but we already know that Malphine has false positives, so now we're going to have to try and narrow it down to see if we can find anything meaningful here. First of all, I didn't really speak about this earlier, but it is written in the notebook, so you can find it there. This notes column is particularly valuable sometimes because if Malphine finds either an MC header, a PE executable header, or a couple of hard-coded function prolog sequences at the beginning of the memory region, is going to be flagged here, and that's going to be extremely interesting to have a look at. So, if there's an MC header or anything at the beginning, definitely look at that memory region first. In this case, there aren't any, so that's not going to be of much value for us for this memory sample. But if there is, definitely look at that first. So that's very useful. Keep in mind that it's only looking at the very beginning of the memory region. So there can still be MC headers, but if they're not flagged in the notes column, they're not at the beginning. It's not something you can use to exclude memory region from your analysis, but it's going to be useful to maybe find something you want to look at first. We can see here that you have the hex dump from the beginning of each memory region and the corresponding disassembly here. But we also have some other indicators that we can use. For example, we learned that process injection usually means that the memory region is private, meaning not backed by a file on disk. We can narrow it down a lot if we just hit this checkbox. We're going to go from 214 rows to just 19 rows. We can also see here the protection flags for the different regions and the commit charges. So all of these have actual bytes to execute. Some of them only have execute read permissions. Some of them have execute read write. If there was anything written to the region by an attacking process, it's going to have read write. So I would want to look at that before I look at just execute read. There are other things you can also do with IBIS to make this more digestible than the raw format that we started with. Like I said, you can filter and everything, but we can also format things differently. To do that, we have to use the UI component that Marimo offers, which is Mo UI table. You can look up the documentation if you want. We just included this little part here about how you can format a column with the function that you define yourself. So this example, I'm just going to show you how it works. This example is pretty simple. It basically just transforms the column, the values of the column to uppercase. So if for some reason you want to do that, you can go ahead and define the function like this. And then we can also just go ahead and define a MoUI table where we pass in the malfind table and we define the formatting like this. And then, as you can see, that is the same table, but just with the process name in all uppercase, if for some reason you want to do that formatting. So that's not very meaningful to do, but it was just an example here to show how you can define a function and then apply it to a given column. So something that makes more sense to do is to, because I bet your eyes were bleeding watching these addresses in decimal format and not hexadecimal. So a better thing to do is to try and do something about that. When you're doing memory forensics, you definitely don't want decimal addresses. So we went ahead and we defined a function for that here that translates the decimal address to a hexadecimal value. And then we applied that to this, the malfind plugin output here. As you can see, we have the format hex address function here, and then we just say that we want to apply that to the address values here. We also dropped 2 columns just right here. So remember we had the hex dump and disassembly columns before. Now we just stop after the notes. So it just makes it a little bit more compact. So that's not to say that those columns aren't valuable, but we're just doing that here. So now this table, sorry, is much better than it was before. We can also do other things, like for example, define a function here that we can use to highlight certain values within a column. So what we decided to do is to highlight the private memory value, the VAD_s tag, and execute, read, write, and execute. So we're just basically looking at if the column name is tag and the value is VAD_s, then return the color that we defined here for VAD_s. And then Marimo is going to apply that to that cell. We also added some other things here to just show how you can play around with the values. If there's something else you want to highlight, like for example, if the region is not backed by a file on disk, maybe we want to highlight that row as we discussed before, now that we know what that means. We also forced the monospace font for the addresses. And yeah, however, to actually be able to apply this function to the style cell argument, we have to have an actual data frame in memory. Up until this point, we only used IBIS table expressions, but that's not going to work when we want to apply something to a row and column. So to do that, we have to run one of these functions. Any of them will work as long as you get a data frame in memory. We went with polars. I'm going to show you right away. So here you can see we did the same thing as before. We used the malfind table here. We selected, or rather we dropped some of the columns, and then we ran 2 polars to get an actual data frame in memory. We applied the formatting like we did earlier to get hex values. And then we applied that function that we just worked on to the style cell argument so that we get this output that you can see here. Other notable things we did here was to, for example, say that we didn't want to show column summaries. If I go ahead and comment that out, you're going to see what that does. In just a second. Here you can see the tiny bar charts that appeared here that maybe you remember from earlier. Oftentimes here in our use case with memory forensics, they don't necessarily make sense, especially when we're talking about memory regions, for example. It doesn't really make sense to display the distribution of start addresses necessarily, or the distribution of PID values. So we wanted to remove that. Another thing we did was to define selection equals none, because if we don't, then we're going to get those tiny checkboxes in front of each row, and we don't want that in this just malfind table output. So that's why we have those 2 rows. There are other things you can do as well, but that's just some of it. So moving on, something else we want to do is to reorder the columns. That's possible to do if you just define the select statement like this. You are going to get the columns in that order. We do return this to a new variable here preceded by an underscore, meaning that it's just going to be defined in this cell. And then we pass that variable to the MoUI table component and run 2 polars, apply formatting. Something else we did here was to freeze the first 4 columns to the left so that even if we scroll because we want to have a look at the disassembly, we're still going to see the process, and these other 4 columns are going to be frozen there even though we can scroll freely. We can also apply justification. So we wanted to have the PID justified to the right-hand side of the column. That's up to you. We just did some modifications here that could make sense. So yeah, that's just some of the operations you can do. We're gonna leave it at that for this malfind table, and this is gonna reappear in our dashboard. We're gonna move on to an exercise now because we also want to have some of the information that we saw while we were exploring the malfind plugin output a little bit manually earlier. We're gonna try and make that visible to the analysts in a intuitive way in our little dashboard. So let's go ahead and look at that. The first exercise is about defining a most stat component, which is going to display a number in a very visual way. We're going to use this first to actually display how many unique processes malfind flagged. We remember there were more than 200 memory regions, but how many unique processes were there actually? So the way most stat does this is that you basically just pass the number you want to display here, and then you can apply a label and a caption. So if we want to do that, maybe you want to try yourself before we go ahead and look at the solution. In that case, pause the video now. You have everything you need to do it, so maybe you want to do it now. Just giving you last chance to pause the video. All right, let's go ahead and have a look at it. This is going to be how it looks. So we're going to define a variable here, and we're going to use the malfind table because we wanted to have a distinct count. We're going to do that on PID and process. Those are the columns. And then we're going to do a count. And we also have to do execute to get the actual data. Let's see if that worked. So we got 9, which is a number. That's good. And now we can go ahead and define the most stat like this and just replace. Actually, we need to do that in the same cell, obviously, because we added the underscore. If we put that in here, and then we can do unique processes, flagged by malfind. Unique processes. Let's see what that gives. So that's a nice little component that we can use, maybe built into something else. If we move on to the next exercise, we're gonna make use of another UI component called tabs, which is gonna allow you to have one little box where you can switch between tabs. So let's say we want to have in one tab the number of unique processes flagged by malfind, and then in the other tab we want the analyst to be able to see which processes were flagged by malfind. And the way you do that is basically this is the MoUI tabs definition, or how you can define that, and then you just put whatever you want in the name of the tab, or like to be displayed as a tab name, and then you pass whatever variable you have that you want in that tab. If you want to try it for yourself, go ahead and do that now. I'm gonna start shortly. So if you do just a distinct, you're gonna get all the columns. If we just want, you can do that too, but in this case, we just wanted to display the process ID and the process name. So we're gonna go ahead and select those as well. Because that was the exercise. So there you go. Then we can define the MOUI tabs. And we have to have these in the same cell again. And then in the first one, we want the unique processes. From malfind. Here, we're gonna do unique processes and count and execute, because we need to just count and display that. And then in the second one, we can do unique processes. I forgot to put a name. Drill down of processes. So here you have a nice little tab component, starting to look like dashboard friendly material maybe. But we obviously don't want just a number like this, but we want the most stat. But we can nest these things, so we're just gonna go ahead and wrap that number in the most stat. We could just copy paste the other one, but I use different names here, so I'm gonna do it again. And you can just put a caption label, number of unique processes, and a caption, go to the drill down tab to see them. And then we're gonna close this and add the comma and run. And then we get the most stat instead of just a raw number. And we can go to this column to see the different columns, the different processes, I mean. So a nice little component for the dashboard. If you remember what we said earlier about the notes column, I also said that that's a very valuable thing to look at. And a good idea in that case would be to check which malfind rows have a value in the notes column. As you can see, we already defined it here. We didn't really create an exercise out of this because it's basically exactly the same thing, but we're looking at a different column. So in our data, we don't have any annotated malfind hits, but if we did, we definitely wanted them to be visible. When you have a most stats component in a tab component like this, you can also write what that actually means in plain English to the analyst. So here we can see regions with MC headers, PE headers, or function prologues at the beginning. There aren't any in this case, but if there were, we wanted to see them and we wanted to display which ones. So here's the code for that. We defined the variable malfind nodes. We filtered on nodes not null. We selected the values we want to have in the details tab. And then we just went ahead and displayed the number of rows from that new table. And we added the whole table in the second tab. Moving on to the next plugin output that we wanted to include, which is suspicious threads. We can have a look at the data here just real quick. As you can see, it has a note for each region about why the thread is considered suspicious. We can see that there are 2 rows for Explorer exe and 2 for OneDrive exe. For the first, or actually for both of them, they have kind of the same verdict in the regions. They both start execution at an address which is not backed by a file, and the address has an unexpected protection string. We're not going to dwell too long on just this, but we're going to want to include it in the dashboard. So we're going to go ahead and do it the same way as we did for the previous components. It's nice to just display how many processes the plugin flagged and also a tab with which ones. So it's exactly the same as before. We also want to create a bigger kind of tab where you can switch between different plugin outputs and show, for example, handles, network connections, that kind of thing for each process that you choose to drill down on. That would be useful to kind of accelerate the analysis if you can select a process and then quickly switch between different plugin outputs and drill down. So the next thing we're going to do in order to make that happen is to create a little drop-down menu for the process IDs. Because, like I said, we want to be able to select the process and then view a whole bunch of things. So first, that's exercise 3, just creating a little drop-down menu for on the process ID. So the Marimo provides a UI component for that too, called MoUI dropdown. In order to get a list of all the process IDs from the memory sample, we're going to do some operations here. You already know about the PS list plugin. This time around, we're using the PS scan plugin. The difference between the two is that PS list walks the linked list similarly to how DLL list walks the linked list for the loaded DLLs. So that can be unlinked, whereas PS scan actually scans the memory for structures that seem like processes. So that's gonna potentially surface processes that have also been unlinked, and that's why I wanted to use it in this case, also so that you can get familiar with both, and maybe why it's interesting to have a notion about both of them. So I'm just gonna go ahead and show the solution here. Uh, you have the right to just go back and pause the video. But what we're doing is just loading the plugin output into this variable here. We're renaming to snake case again, and in the PS scan output, the process name is under a different column name called image file name. So that's why we're doing this operation here, renaming process to image, or we're taking the column called image file name and calling it process instead. Next, we're going to do a filter on the processes where the PID is not null. And then we're going to do a distinct count, order by PID, because it's just much more easy to scroll through the drop-down menu if they're actually chronological. And then we're doing the 2 pi arrow operation to get the actual data frame. And then we're doing 2 pi list to get a list of dictionaries. So that's not a regular array, but it's a list of dictionaries at this point with just the different PIDs. Next, we're iterating over that dictionary and we're extracting the values and we're assigning them to this variable here, PID list. And then we're concatenating the value all at the beginning of the list so that you have the option to choose all processes and just view all network connections, etc. And then we're using this options variable and sending it to the MoUI dropdown component. And we're setting the default value to all, and we're giving it a label, filter by process ID. So that's what we're getting here. As you can see, there is a list here of all the processes. You can select all. That's what it's gonna be if you just start a notebook, but I already looked at it earlier, so it was 7824. You're gonna see why shortly. But at least now we have this drop-down menu that we can use in our uh, tabs component that I explained just before. Next, we're going to go ahead and load the output from a bunch of different plugins and rename to snake case. As you can see, we have VAD info handles, netscan. Netscan does a similar operation as PS scan. It scans for network structures in memory, network connection structures. We're also using LDR modules and DLL lists. This is just arbitrary selection from our side for this notebook. It might not be what's best in all cases for memory forensics or process injection detection, but we're just choosing some here so that you can see how it looks, and then it's just a starting point for you guys to build your own apps for this use case later. Here we introduce a function where you can filter based on the value from the drop-down menu. If it's all, then we just return all the data. But if it has a value different from all, then we're going to filter based on that value on the process ID column. So we're doing that on all of the tables here, and we're getting filter tables. And if you go ahead, okay, let's see, now it's set to all on in the drop-down menu. So you can see we have network connections from different processes. If we go ahead and change that to, I hope this one has network connections. It doesn't, but you can see that because of the reactivity, they are going to change. When you just change the value of the drop-down menu, you're going to get a different table actually. So yeah, let's move on and look at the handles plugin output a little bit. As we were preparing this notebook, we looked at all of the plugin outputs that we're using here, and we noticed that it might be interesting to look at a couple things here. Let me see if I can just show you guys the handles. This is just the non-processed table. You can see it has the little bar charts and its decimal addresses and that kind of stuff. We can also see that this might be interesting to have a look at because some values are reoccurring. You can see the types. Maybe you want to filter on just handles to a process like we saw earlier. That's typically something that happens when a malicious process is trying to inject code into a legitimate process. It opens a handle to the process. So maybe that's something you want to look at. Maybe this means something. So there's like uh, almost unlimited amount of things you can try and dig down into when you start looking at the data like this. If this has a particular meaning, maybe we can render it differently. Maybe this means something. Actually, this doesn't mean anything. This is just the incremental value. So I can just spoil that to you right now, but this means something. So we did create a function here for highlighting some values in the handle's output. For example, uh, the granted access field, as you can see here, we wrote down some things here that for process hollowing, the handle to a process requires at least write and process VM operation, which gives a certain mask. This is a decimal value, mind you, so we're going to also try and get hexadecimal values instead. But that's just like a very short explanation of why we're doing some of these operations here. So the highlight handle indicators function here is going to highlight handles to a process, and it's going to highlight also if the handle is to a different process than the process itself. So that's the meaning of this if statement. And then we're going to force monospace, and also in the table statement down here, just jumping down here a little bit to not lose the thread. So we're going to apply the hex address formatting to those columns that have values that should be in hex, like offset, which is an address, and then this granted access, which is like a list or like a sequence of flags. Yeah, and then we're going to apply the handle indicators highlight function. So for all the other tables as well, we didn't do as much work. This is still like something you can explore on your own, but we did apply the hex address formatting to all the address columns in the different tables. And then we used the tabs, the MoUI tabs, to just put all these tabs one after another in a huge tab here. So right now, the drop-down menu is set to 7824 as we did set it earlier. If I change it here, the other place where this drop-down menu appears is going to change as well. For each of the tabs, we added both the drop-down menu and the table so you can get them in the same view, and you can change the drop-down menu as you go. So that's why, as you can see, uh, these are using the V stack. The only tab that doesn't use that is because in the PS scan, we didn't find it very meaningful to choose just one process ID because the PS scan output shows all the processes. So you can find the process ID of the process you want to find. Moving on, we're going to go ahead and look at the info plugin output. This plugin shows us some interesting details about the memory sample. Might be interesting to include somewhere. So we wanted to just include an exercise here where you get to take this and present it somehow. So feel free to pause the video and do that now. I'm just going to go ahead and show you how we did it. So basically, we just used the MoUI table component and wrapped it in an HTML div with the fixed width. So nothing crazy here, but it's also cool to show how you can use HTML directly in the notebook. And next exercise, we are going to ask you to show overlap between two plugin outputs, specifically in this case, malfind and suspicious threads. So we wrote a function here where you can input two plugin output tables and find the overlap based on the process ID and the process name. So we're just going to give both tables to the function and then return the join on process name and process ID. and then select just those two columns and do a distinct count. So when we do that for malfound and suspicious threads, we get OneDrive exe, and we've been seeing that a couple times now. So as you probably also think, this process warrants a bit of a more thorough investigation. We're not going to go ahead and reverse that here, but if this was an actual incident, you would want to look at those memory regions that we saw in the suspicious threads plugin and in the malfind plugin and dump those and then run Yara and strings on those. If you find an executable in any of those regions, for example, we already know that there's no MC header at the beginning. Maybe there are still MC headers or something like that, but not at the beginning. Maybe there's some junk in front of it. If that's the case, try and remove that junk and then open it in a disassembler or something if you find an executable, because you would want to reverse that. We can also examine this process by looking at the other plugin outputs like we have in our tabs, our huge tabs UI component at this point. Just select the 7824 like we did and drill down on the different plugin outputs like network connections, loaded modules, handles, etc. We definitely have a clear lead here in that process, so that would be the logical next step. You could also use that same function that we created for finding overlaps to find overlaps with other things. So if you want to see what kind of network connections are made from all the processes flagged by Malfind, for example, you can do find overlap between those two tables like we did right here. For example, if we want to drill down on what kind of network traffic was initiated by the OneDrive process, we can do something like this. It's nice to work in notebooks like this because you can have all the data you processed still available. It's not like being in a terminal where you just run some grep in a text file, then you exit it, you find something else. This is like pretty nice actually for instant response because you can also export the whole notebook as and download it as HTML, and it will hold all the tables and everything that we're seeing now. So that's very nice for documentation. But anyways, if this was a real incident and you have like reason to suspect that OneDrive has malicious code running in it, and you see that it has a network connection to this IP, maybe you would want to look into that. I just want to say that like don't poke infrastructure if it's a real incident. In this case, it's fine. It's just a test sample that we created, but you definitely don't want to start poking around on attacker infrastructure. Also, obviously, OneDrive might have network connections in its legitimate state as well, because we all know OneDrive, it's backing up files for us in the cloud, so that is not necessarily an indicator of that IP being malicious, but you would want to check that out still. So last exercise that we're going to look at here is just using the different components that we've made so far and building a dashboard with them. So Marimo makes that pretty easy for us because we can just toggle to app view over here. When you first toggle to app view, you're going to start with a clean slate, and then everything you output in the notebook is going to appear on your right-hand side here. So I just found the elements that I wanted to use to put together this dashboard real quick. You probably remember the Malfind tab view here that quickly shows the stats about how many processes were flagged by Malfind, how many of those had any MC headers, PA headers, etc. and the little MoUI stat here with suspicious threads. And then I also put the overlap between the malfind and the suspicious threads. And obviously, I wanted to include the huge tab here with all the stuff that we put together in different tabs so you can drill down easily. Uh, and we got the formatting that we put in place earlier and all that. So, and you can filter on PID. All that is just like in the notebook. And the magic part comes now. That's you can go ahead and save the file. The cool part is that when you do this, you're going to get a new file in your layouts folder in the repo. It's going to be a .grid.json file, and it's going to have the configuration of all the things that you positioned in your app view. And then you can actually go to the root where the notebook is, and you can run instead of editing the notebook, and that's going to run it as an app. So just imagine the whole workflow here, how much you can automate. You have a memory sample, you automate the running of the different plugins, you export to Parquet, and then you spin up this app here, and you can see information like this easily. And you can work with the data, and your analysts are going to be supercharged with the useful information here and make them much more efficient. So this dashboard here is just super quick what I threw together with the different things that we work with in the notebook. It's just to spark ideas for you guys. Would love to see what you come up with as improvements or other tangents or whatever, but just want to show how cool and easily you can make little apps for memory forensics. So that's it for this notebook. Hope you guys enjoyed it and that you're ready to attack the next part.